I'd like to start this lecture with a quote from Michael Berry, because I'm going to be talking about this Berry phases mostly that you heard about last time. And this is actually an interesting quote, which I will use to kind of set up the tone for the discussion. So if you go to that book, Shapir and Wilczek, Geometric Phases in Physics, you go to the sort of first entry there by Berry, and what you read is that examples of geometric phases abound in many areas of physics. Many familiar problems that we do not ordinarily associate with geometric phases may be phrased in terms of them. So basically, now I can show you the main part of this slide. You do not need that at all. So all this Berry phase business, Berry curvature, whatnot, you don't need it. Okay. And this all can be done using some sort of quantum kinetic equation, and all these effects are effects of a so-called interband coherence. Okay, so you don't need to know anything about this geometric stuff to actually solve problems. Right, yeah. So wait. Actually, Sir Michael Berry kind of saves the day. He adds that often the result is a clearer understanding of the structure of the problem and an elegant expression of its solution. So basically, he says that if you're not dead inside, you will sort of like when it's done, in a geometric way. So this is actually a typical way to solve problems. It had, it used to be like that. So you actually do the honest calculation using, Kubo formula or, quantum kinetic equation. And then once you solve it, you basically don't tell that to anybody. You say, oh, look, this is geometric, stuff, phases. You interpret your result that way. But of course, now nobody solves, a quantum kinetic equation. Everybody just slaps these phases in the Berry curvatures right away, and nobody knows whether the results are correct or not. But nevertheless, remember that in principle you don't need that. There are ways to check yourself and not make mistakes. And this is sort of the attitude I will take in this lecture. I'll kind of show you things, places where it's easy to make mistakes, and mistakes were made, and how to fix them. And I think it's a useful exercise because I don't know what the exact percentage, but 80% of your time is really devoted to checking yourself, looking for mistake, correcting mistakes, making sure you do not make mistakes. So having some checks, to use. In that process is kind of nice. And I hope to make it to Onzaga relations. These relations are probably the most violated in the entire history of physics. The trick is to violate them before you publish, right? And realize that you did that. But it doesn't happen always, so I got lucky that way. But okay, so just a brief recap of what we talked about, we meaning us as a group, not just myself. We talked about last time we talked about this, a classical description of electrons where band energy is promoted to the Hamiltonian of the particles, and you get canonical equations of motion, and then maybe I will get to Boltzmann equation to discuss how this is used. Okay, then it turns out that there are corrections to this picture, and you've heard about these corrections in every lecture. Okay, even in the lecture by experimentalists, right? But let me say it once again. Okay, and Maya told me that we learn by repetition, so I'm good just repeating whatever was said in the previous lectures. But there is a point to that, I promise. So first of all, I just want to say that all these expressions for the coordinates of a particle that you have seen, they can be obtained quite straightforwardly from just basic quantum mechanics. There is nothing particularly fancy about it. Okay. So what you do basically, you see how the operator of coordinate acts on a wave function written in the basis spanned by the Bloch states, right? You're trying to get the representation of the operator, the action of the operator in the representation, spanned by the basis of Bloch states. And I will not go through these exercises; they're obviously in the notes. But you essentially substitute R with k derivative of the exponential. And then, because there is summation, you try to get this, you try to get the operator acts on the wave function These are these coefficients, C and K, in this representation. That's what defines the action of the operator. And essentially, you just, it acts, of course, it has, intra-band matrix elements, inter-band matrix elements. You just keep the intra-band only, okay? And boom, you will get your expression, okay? Why did I repeat that? I repeat that to emphasize that what you have here on the left is a physical coordinate of the electron. It's the actual coordinate of that electron, while the canonical coordinate is what Professor Ong called the lattice coordinate yesterday. That's the one that is conjugate to the quasi-momentum of the electron. And this is going to be important later when we talk about these densities of states and things like that. Okay. So just a quick word on this semiclassical motion. Why motional? Semiclassical, motional, semiclassic motion in external fields. Okay. So basically, after this exercise that we have just done, you have a operator for the physical momentum. This is the physical, kinetic or whatever momentum. Okay, we have the not operator, just expression for the physical coordinate. Again, these are the canonically conjugated pieces. Okay, and you just write down the equations for the motion in external fields. Okay, and you get what David already showed you last time. Okay, so basically the equation for the force is what you expect. And you see the structure here is very, very symmetric now. Okay, you have connections both in real space and momentum space. So you can proceed by experience, essentially, if you've done that already. So the motion in momentum space, velocity in momentum space has the usual, electric field piece and magnetic field, the Lorentz magnetic part of the Lorentz force part. But then the velocity, in real space, then has gradient in momentum space part and sort of magnetic field in momentum space piece that looks like Lorentz force, but in momentum space, and it's determined by the magnetic field in momentum space by the Berry curvature. Okay, so. There is really no point in reminding you how anomalous Hall effect stems from that, but there is a reason I have this here. So if you set magnetic field to 0, okay, so there is no magnetic field, you can only get anomalous Hall effect from some sort of magnetization. Basically, it will come from the Latinger velocity. Okay, we call it that from now on, from this piece. Okay, but basically there is this minus sign. I'm not sure why everybody dropped that minus sign. It's actually minus integral of the Berry curvature, not plus integral of the Berry curvature, which has to do with this, cross product, and of course the order of indices that you put on the left. So you either write down sigma xy and it's minus Berry curvature, or sigma yx and then it's plus Berry curvature. Okay, so and these pluses and minuses are important. So basically, another reason I included this is to emphasize, sort of a little bit in the spirit of the talk by Fan Ong yesterday, that this this derivation of the anomalous Hall effect, it took 30 seconds of our time. Okay, but historically, Hall, who discovered the Hall effect. This is actually a rare phenomenon when Hall discovers Hall effect. It's like Planck's constant is introduced by Einstein. It's always like that. Okay, so basically it took some 70 years to figure out essentially where it came from, the origin, the spin-orbit coupling. Okay, and you can compare it to the BCS theory that took 40-something years. Okay, of course fewer people I guess had been working on the anomalous Hall effect, but this is very hard. Okay, so this tiny expression took several decades of brain activity of very smart people. So it looks very simple now, but in reality, it's very, very hard to get to that. So another quick word about what Jen started talking about the how this anomalous Hall effect basically shows up in wireless metals. So you can try and play the same game you do for two-dimensional anomalous Hall effect. You can do it for three-dimensional. Hall effect, right? So the idea is the same, right? What you need to do, you need to integrate Berry curvature over the Brillouin zone. Okay, that is unchanged. So I deliberately didn't put any kind of distribution function here, right? Occupation number. So I'm basically at 0 temperature in the ground state, filled bands. I don't have Fermi surfaces right now. Okay, so just to show you explicitly where that weird Hall effect comes from, basically let's do this very strange exercise. Let me write omega A, okay, Berry curvature with a Cartesian index A, as omega b times delta AB, and write this as, dKA by dKB, okay, which is a very strange manipulation. But what it allows you to do, it allows you to integrate by parts and move this differentiation onto the Berry curvature, okay? So and then this is actually integration by parts like that is very questionable because you have to take into account the boundary term, okay? And the taking into account of the boundary term basically makes what will appear on the right defined up to a reciprocal vector. Actually, this is, I put here a question mark because this is not a question mark. This is incorrect in general, okay? So what you can show this way is that basically this Hall effect is essentially an integral of over the Brillouin zone of Ka times the divergence of the Berry curvature. Okay, so wherever there is a Berry monopole, right? So you have, remember in the Weil semi-metal case, every linear band touching is a Berry phase monopole, Berry curvature monopole. Okay, so just like divergence of electric field for a point charge is delta function of that point charge location, divergence of in K space of Berry curvature for magnetic charge as delta function of the location of that magnetic charge. So that's where you get this dipole, moment in momentum space. It's not the same as Berry dipole that again David mentioned. Basically, see that I have to go through the entire Brillouin zone and see where I have magnetic monopoles and sum the wave vectors of these monopoles to get the Hall effect. Okay, and again, what I get is defined up to this. Essentially, I get a Hall effect that is proportional to some reciprocal, not reciprocal, just reciprocal space vector. It's 1 over length. That's what I mean. Okay, it's a K vector. Okay, but this K vector is defined up to a reciprocal lattice vector of the lattice, which I cannot get from this kind of derivation. Okay, I need to know the entire band structure and the entire Brillouin zone to actually get that piece. Okay, so this was essentially worked out in Haldane's famous PRL and was a subject of some discussion when these Weil semi-metals came around, and some things were said that shouldn't have been, but by now it's established what this is. So let me now abandon Hall effect for a second and actually see what we get from these semi-classical equations if we add a magnetic field. Please. So microphone, all right. So obviously you have to ask your question, but it's going to take a while this way.
I'm sorry for that.
No, you're fine. It absolutely has nothing to do with you.
No, because you won't get through your notes otherwise.
Use the microphone now.
Okay. So you just called it a monopole for the Berry curvature.
Yeah.
So I was just, because I've never heard that term.
Right.
And
I just made it up, to be honest. And it
okay.
coincided with what David said. It was very unfortunate.
Yeah, so, okay, sorry.
Because it's a different object.
Okay, because I was thinking if it is like a relation to, normally you would also say like, okay, you get like charge. It's also like a source for something. And I was like...
No, that way it's very similar. You do get this, effective charge, magnetic charge, fake magnetic charge from these monopoles. Yeah. And then you see it's like a dipole moment where instead of R in real space, you use momentum in momentum space. It's actually way more Berry curvature dipole than what it's defined to be in the literature. So this is dipole thing. And, Liang Fu and Inti Soderman called it like that. So, okay.
Okay, thank you.
Right. So when you ask questions, make sure you're located at different corners of the room because it's more fun that way. Right. And we're going to exercise. Right. I can do that too. I can repeat your questions.
Sorry, just to make sure I understand. I mean, there's no you talk about an ambiguity in K,
Right.
but there's no ambiguity in sigma, right? That's a measurable quantity in the lab.
No, right. So what I'm saying is that, sigma is what it is.
Yeah.
So I want to calculate it. And from this exercise that I did, I won't be able, in general, to recover what it actually is. So in that sense, it's ambiguous. It's not ambiguous. It is what it is. I just cannot find this, reciprocal vector piece of it. Okay. So let's move to these things. Actually, let me poll you a bit. So, like, how many of you know what chiral magnetic effect is? Just to see. Oh, perfect. So, no, not all of you. Okay, great. Actually, a great minority of you know that, which is perfect, obviously. Okay, so let me just take these equations and sort of run with them. Okay. And again, as David mentioned, you see that P dot and R dot, they appear on both sides of these equations. So I really need to solve for P dot and R dot. It's these equations are not the final product. And when I do that, I encounter strange things. Okay, so of course, let's talk about the force. Okay, P dot. Of course, we have the usual electric field, right? We have the magnetic force acting on the electron because it has band velocity. But then there is this weird beast which has E dot B in it, okay? And this term is multiplied by the Berry curvature, okay? So if you look at it a little bit, it looks very, very strange. So let me actually draw this. So what is this force? Where does it point? Imagine that there is the origin of the momentum space, and I will see where the force points. So for a while point, remember the Berry curvature, actually it's also for conduction band of plus chirality, it's minus 1/2, not plus 1/2, 1 over p squared. But, who cares, right? Right, so the point is that it points along the unit vector, or along or opposite to the unit vector along P. So if you look at what this force does, if E dot B is not 0, right, if you have a configuration of electromagnetic fields in which E is along B, what it does is the following. So the particle here, let's say we are in a conduction band of positive chirality while point, basically there is this minus and E dot B, let's say it's positive. So there is a force that pushes it this way. Okay? For this particle, there is a force in quotation marks that pushes it this way here. You see there is this radial push, okay, that basically takes the particles and moves them radially away from the origin. Okay? And that happens, of course, for any sphere really around the origin. Okay, so if I integrate this whole flux of particles because of the force away from the origin, because of this 1 over p squared, things will cancel, and you will see that there is a constant flux flowing away from the origin. Okay, so it's like there is a source of particles at the origin that you cannot see here, right? Which are then accelerated away from it. It's like there is a I don't know, this bathtub. How would you call this? Inlet of a bathtub from which these particles are flowing. Source, right? Okay. If I remember these while points, they come in pairs. So for the other while point with the opposite chirality, it looks like there is a sink of the particles at the origin. Okay, which looks very weird, and basically. This is the condensed matter version of what is known in the high energy physics as the chiral anomaly. So if I disregard the other while point, I will only look at this one that I just indicated. It looks like the particles are appearing out of nowhere. Okay, and if I look at the other while point, they're disappearing into nowhere. Okay, so for each while point separately, the number of particles near that while point is not conserved. If you look at the Hamiltonian of the while point, it absolutely sort of commutes with the number of particles near that valley. So this is the situation that referred as anomalous. If your dynamics breaks the conservation law of the Hamiltonian, you say that there is an anomaly in the problem. Okay, so I will interpret this. It's actually very, very simple, no matter how mysterious it may look. It's extremely simple in condensed matter context, or solid state even context. But I would like to go through a couple of other things before I do that. So there is the, if we look at the velocity parts, there is the famous anomalous Hall effect, the anomalous velocity. We call it Leitinger velocity from now on. Okay, but there is this another piece, which I will call the chiral magnetic effect, which is a very strange velocity. Okay, so again, if you look at this r dot, this Berry curvature points either along v or opposite to v. Okay, so this dot product is essentially angle independent for an isotropic wild point. So you see that there is a velocity that points along b. Okay, you apply magnetic field, and there is basically a component of the velocity for a wave packet that just points along b. You're not used to that situation, right? You're used to velocity being, along momentum, opposite to momentum. Maybe if things are anisotropic, little bit at an angle to momentum. But this does not depend on momentum at all, right? It just goes along b. Okay, and we will see that this leads to the so-called chiral magnetic effect. So this final thing I would like to say is the appearance of this factor dB. I use the notation with electric charge being negative, so it is actually what it is. So that's why there is a minus sign as compared to David's notation where E was positive. Okay, that actually creates a gigantic mess in the literature because if you specify what you use and you use it consistently, you're fine. But people never say what they use and actually use two different notations in the same paper. Then things become weird. Okay, so. This density factor, density of states factor, basically appears because P and R are not canonically conjugated. So these equations are not Hamiltonian equations. Okay, so because of that, if you look at the phase space defined by P and R, the volume in that phase space will not be conserved in dynamics. So in order to conserve the volume, you need to take dr dp and multiply it by this correction factor, and that is the conserved volume. That is what that's what satisfies. Liouville theorem and things like that. That's the origin of this factor. Okay, so let's interpret briefly these weird things that we have seen, and they all actually follow very easily from the Landau level picture that we sort of talked about yesterday. You're very quiet. Is this clear what I'm saying? You usually ask a bunch of questions. Am I confusing you completely, or I'm so clear that there are no questions? Please.
Since you're asking for questions, could you go back one slide,
Sure.
Where the chiral anomaly is?
Yeah.
Now that, sorry, I'm not familiar with this, but that goes like E squared. So presumably an electron in a hole would suffer the same effect.
Yeah.
And yet, if I brought the electron and hole close to each other, I would have something that had no charge, and then there should be no chiral anomaly.
No. Let me go through this, Landau level picture, and I think it'll give you an intuition of why it's a spectral flow essentially from the valence band into the conduction band. So it is actually the same for electrons and holes, if you will, and you'll see that. Okay. So remember we talked about the Landau levels for a while. Fermion. We mentioned that it's really graphene and PZ dependent gap for B oriented along the Z direction, and the Landau levels for this problem essentially look like that. There are these levels with n not equal to 0, which disperse the way you expect Landau levels to disperse in 3 dimensions. But then in each valley, there is a chiral Landau level. Okay, again, Philip mentioned it last time. Okay, there is a chiral Landau level with opposite chirality for the opposite valleys, which basically does not do that. It actually all these electrons, all these particles go in the same direction near a wild point, but of course somewhere deep in the bottom of the band, these two Landau levels, chiral Landau levels, are actually connected to each other. So if you will, there is one special zeroth Landau level that is a very non-local momentum space. It goes from one wild point to the bottom of the valence band to the other wild point. And this is the string that kind of connects the two wild points. Okay, so let's see what happens here with this string. So imagine that I turn on now electric field along the magnetic field. Right? Remember, E dot B should have been non-zero in that construction that we talked about. So what will happen is that these electrons will get accelerated. Right? They have velocity along the electric field. Right? They will increase their energy. Okay, these electrons will get decelerated. They will slide down the dispersion. So basically, you will have this sort of a sausage of electrons kind of doing this. Okay, right? So of course, you interpret that as if you do not look at the bottom of the band, if you decide to be blind compared to this part of the dispersion band structure, then it does look like electrons basically are disappearing from this point and they are reappearing at this point. Okay, but you know this being blind to this part of the band structure actually did lead to mistakes. Okay, if you try to work only with a low energy theory and you do not know how to properly regularize, this infinite Dirac sea, if you will, you'll make mistakes. So we'll talk about that.
Very basic. Why the Fermi levels are different? What is mu?
That's for later on. I just wanted to emphasize here that they can be different, and that's the origin of the chiral magnetic effect. There is no need for them to be different at this point, but I'll comment on that.
Thank you.
Okay, let me take a sip. So maybe another word on why it's E dot B, not just E, the way I described it. The reason is that basically acceleration of the electrons, the rate at which they arrive here and at which they disappear here is proportional to E, but how many electrons you have on this zeroth Landau level because of the degeneracy of the Landau level, right, is proportional to B. And I said that E is along B, so that's how E dot B comes about in this picture. Okay, so if you're a little bit experienced with these things, you can actually object, because when you talk about classical transport, it's a situation where you decide not to resolve these Landau levels. You say they're actually not formed. Why you're talking about them? What about a very strong disorder that scatters the electrons very, very strongly? Landau levels are not formed at all. Where is this chiral anomaly in that case? You see what I'm saying? It's a very idealized picture, right? With the perfect translational invariance, that Landau levels are formed, no scattering. So the point is essentially gauge invariance here. So imagine that I add to this picture lots and lots of impurities which do not scatter between the two wild points. You see what I'm saying, right? So basically, electron that is here can be scattered here by the impurity. But so for now, I do not consider processes that take you from this part of the momentum space to this part of the momentum space. Okay, which of course does happen, but I just disregard it for now. Okay, so the point here is that even if you add impurities and all of this is messed up by the impurities, essentially charge conservation, gauge invariance, tells you that you cannot stop these electrons. Okay, basically with impurities you have a scattering problem with two channels that move that way and 3 channels that move this way, and basically charge conservation tells you that you cannot stop. You cannot repackage 2 electrons into 3 electrons when you scatter. Okay, so there will always be this extra mode that goes downward in this valley, and there will be extra mode that goes up in this valley. It will not look at all like this Landau level that I described, but there will be overall motion basically in the opposite directions. Okay, so that's just unitarity of scattering that guarantees that. So can we interpret the chiral magnetic effect using these Landau levels? Absolutely, and that's where the different chemical potentials become important. So now imagine that instead of having, if I drew it with a common chemical potential, I draw different chemical potentials in the 2 valleys, right? So the question is, how large is the effect? And this is absolutely a reasonable question. So the rate of change, I should have said that, the rate of change of the difference in the number of electrons in the two valleys, okay, is proportional to E dot B, okay, and a bunch of fundamental constants. Whether it's large or small, I cannot really say because it's a dimensionful quantity. Okay, so I will have an example. That will sort of tell you how large of an effect it can lead to. This, negative magnetoresistance, and you'll see that it's actually very hard to make it large because essentially it's a fight over a single Landau level versus many conventional Landau levels. So to make this Landau level work, to make it be a player in this context, will be very hard. So we'll get back to that.
You assume that here the electric field, magnetic field are independent of time, and they do not vary in space.
Right. So that's important. So in this context, I take the electromagnetic fields as just non-dynamical sources essentially. So if I were some sort of high energy theorist, I would actually look at E and B that were dynamic, that would be fed by the electronic behavior, and then there are some weird things that can happen too. They will never happen in condensed matter context. They can maybe happen in quark-gluon plasma or in some astro scale field, but not in crystals. So we're safe that way. Okay, so coming back to the chiral magnetic effect, it's also a very simple thing. Remember that there was a velocity that pointed along the magnetic field coming from those semiclassical equations. And it's also very much clear from this diagram where that comes from. So basically think about the two valleys being filled to different chemical potentials. Okay? So the number of electrons in this valley is slightly different than the number of electrons in this valley. Then I'm assuming that otherwise the electrons are in equilibrium. So they're in partial equilibrium. They're in equilibrium in each valley, but the two valleys are out of equilibrium with each other. So in this valley, this chiral Landau level is filled basically to this level, and here, let's say I should have put it like, here to this level, okay? So the number of down movers here is different from the number of up movers here, okay? So obviously there is a net current along the propagation direction of this chiral Landau level, which is along the magnetic field. Okay, so if the chemical potentials in the two valleys are different, then you have a net current. That is proportional to the chemical potential difference between the two valleys and flows along the magnetic field. This is the famous chiral magnetic effect. Okay, so in particular, static chiral magnetic effect. I can also apply a magnetic field at a finite frequency. And then all of a sudden, this coefficient 4 changes to a coefficient 12. Okay, this is another tricky place here. It turns out that this reduction by a factor of 3 is an effect of that magnetic moment that I mentioned some time ago yesterday. Okay, so if we get to that, we'll discuss that. If we don't, be aware that there are tricky things happening at finite frequencies here. Okay. So this is really at frequencies large compared to inverse relaxation time in each valley. Okay, so this is not at any frequency. So maybe I'll just skip that. So just remember that this chiral magnetic effect is proportional to the chemical potential difference between the valleys, and that if you have many valleys, you have 24. Okay, then what you need to do, you just need to go from valley to valley. Basically note its chemical potential, multiply by its chirality, if you will, or Berry charge, okay, and just go for over all valleys. If this sum is going to be non-zero, you will get a chiral magnetic effect. So that's the generalization to any number of nodes. Okay, so now sort of a fun part of this story. Now, you all somehow love symmetry, it seems, from Jen's lecture. So let me do the following. So remember, the situation I have been considering so far, please.
Yes, so for this chiral current going from one whale point to the other,
No, it flows in real space.
it flows in
It
real.
flows in. So I have a sample, right? I have a sample. No need to draw this, right? I have a sample, basically. In this sample, in the real space, there is embedded a momentum space in which the action happens. But basically, some electrons in this momentum space, they flow down. Magnetic field is this way. And, more electrons, for example, flow up. So overall, when I sum over the entire momentum space, I get current in real space that flows along the magnetic field. Okay, so you have to live in both spaces.
Okay.
Okay.
Yes, exactly. Yeah, good, thank you.
All right, sure. That makes sense to ask that, yep. So, yeah. So far, at least, implicitly, I've been assuming that my while points are at the same energy, right? So as you know from Jen's talk, that is a situation where a time reversal inversion is broken, but inversion symmetry is preserved. Okay, so then I guaranteed inversion basically tells me that if there is a while point at k, there is a while point at minus k with exactly the same energy and opposite chirality. Now, let me break the inversion symmetry. What it'll do in general, it'll just displace the while points in energy, right? One will go up, the other will go down. There is no reason for them to be at the same energy anymore. Okay, so you do this. Okay. Then something weird happens. Now, is it noticeable in the drawing that, the position of this while point is different from the position of this while point? So this is the axis of energy. Okay, this is my handwriting, if you wanted me to write. Okay, so look what happens here. It looks like if you count from the position of the while point, even for a common chemical potential, everything is in equilibrium. Okay. It looks like there are definitely fewer of these electrons as compared to these electrons, right? They have different chemical potentials accounted from the while point, right? And it seems I just told you that if these chemical potentials are different, you're supposed to get a current. Okay? Of course, I should to make sure there are no confusion about it, there is no such current. Okay, so to imagine what it would do is completely pointless. It doesn't exist. Okay, but at least naively, if you just look at low energy theory, you say I'm going to live within this low energy theory, here and here. Okay, and it actually very much depends on how you define this here and here. Okay, it seems like you should get a current. Okay, and this is actually a very there were papers written on that. Then papers written on why there is no such current. It's actually very tricky to see why there is no such current. How do you start here? Okay, you start. Okay, we're in equilibrium and there is a current. So this is not something you come by every day, right? So you start to scratch your head. So we know that there shouldn't be a dissipative current in the equilibrium situation, right? There is no there's no push. This current flows around, along magnetic field. It's not dissipative. It just flows, does not dissipate any energy. That criterion fails. What do you do after that? What kind of checks would you run? I mean, this is your life. If you cannot do that, you're done. You have to run all these checks when you get an answer. It's a simple answer. So let me put it down for you. There is a current that is equal to some constant times B, okay? So you have to decide why it looks weird. We decided that it looks weird because it flows in equilibrium. Presumably, it doesn't. There is no such current. Why else does it look weird? So what needs to be running in the back of your hand is the tensorial nature of things, right? It's the symmetry properties of various quantities. So the current is a polar vector. It's a real, usual vector, right? The one that reflects in the mirror the way you expect it to reflect in the mirror. Okay, this thing is an axial vector, right? It's a pseudo vector. It reflects in the mirror not the way you expect it to reflect. Okay, it does the opposite thing as compared to the polar vector. So you see that the transformation properties of this vector are different from the transformation properties of this vector. Okay, so if you want to have a linear relationship between these, right, the symmetry that is different, that they transform under in different ways, should be broken in the crystal. But it also doesn't give you anything in this case because, yes, we broke inversion, which separates them, okay? So we actually are allowed to have a relationship like that, okay? This test also fails, okay? It's allowed by symmetry. What else is left? I mean, this is an unreasonable question. It's impossible to guess. But maybe? So right. So basically, usually when you say tensor A is equal to tensor B, okay, the transformation properties of A and B should be the same. It's principle of somebody, I forgot, but basically, if there is a equality sign, they should transform the same way under the symmetries of the system. Okay, so basically, if the transformation properties are different, right? I do inversion transformation, and this thing flips, and this thing stays the same. That means that inversion should not be a symmetry of the system. Okay, it should be broken. Okay, if you will, lambda basically is proportional to, naively, this E left minus E right, which is the strength of inversion breaking in this case. Okay, so that's in that sense, it's also very reasonable. Okay. So when all tests have failed, there are two left on Zaga relations or gauge invariance. It turns out that on-Zaga relations have nothing to do with this particular case. Okay, so it's really gauge invariance that forbids this current, or common sense. But the way to see it is like this. So basically, if you say that J equilibrium is proportional to B, you have to remember that J is basically minus. If we're in equilibrium, there is free energy, okay, and you can get current by varying free energy with respect to the vector potential. So we know that basically there is this kind of derivative, and it's proportional to B, okay. But at the same time, we can vary this free energy with respect to B and get a constant. But basically, this means that derivative of free energy with respect to B is magnetization. So we get dF by dB magnetization. Magnetization by dA is equal to constant, lambda. That means that there is essentially, okay, I wrote it in a super weird way. So let me just erase this and say that basically this in equilibrium implies that there is magnetization proportional to the vector potential, okay? And since vector potential basically is not a gauge invariant quantity, you know that this is not allowed in a normal metal. Okay, actually, this would have been allowed in a superconductor where the vector potential is substituted with this gauge invariant phase gradient. Right, it's a really grad phi minus vector potential, and then in a superconductor this is perfectly allowed, and this is nothing but supercurrent induced magnetization. Okay. So that is fine in a superconductor. That would be forbidden in a normal metal. Okay, please.
I think there's another answer and a simpler physical answer, which is that if you simply make a slab of this material and put a magnetic field in the vertical direction, right, it says it violates conservation of charge because it puts charge at the top surface indefinitely.
Right. And what is the physical basis for gauge invariance? Charge conservation. Right. Yeah. Right. So no, you're absolutely right. Yeah. So basically, that's a way to get a feeling that this current is weird. It just cannot flow. Okay, but then maybe I should mention that people who discuss that, they say, okay, it flows and goes into the surface, and maybe it's some sort of polarization current, and it goes around. So you can kind of convince yourself, even using that argument, that it does exist, except it does not. And after this, game over, basically. Okay, there was a hand up somewhere.
Yeah, so now I have a very naive question. So it might sound stupid, but now we discussed like this current, which like coming from this chiral anomaly and
chiral magnetic effect, technically.
Yeah. Okay.
Right. Mm-hmm.
Okay.
Yeah. And again, it doesn't come from there. It's zero, but please. Right?
Which brings me to my question: why do we look at it now? Because if it's
just because we want to publish in Nature Physics, right? It's a current. It's a platform for for writing many more papers on this kind of currents.
Exactly. Can you give me a perspective why we want to look?
No. So look, I mean, I can give you a physical
Thank you
perspective on this. So this all actually comes from quark gluon plasma, okay? Where when you have two nuclei, two protons, two nuclei colliding, they collide a little bit off center always, okay? So basically, what you get there, you get gigantic electric fields, just because it's that kind of physics, and also you get magnetic fields because the collision is off center, okay? So in principle, there are configurations with E dot B being non-zero, okay? And what these currents can lead to, without any inversion symmetry breaking, it's really high energy context, right? They can lead to a phenomenon of chiral separation, right? So the quarks with different chiralities will get somehow drawn to the different parts of this mess, quark gluon plasma during that collision, and apparently it leads to some observable effects, okay? So that's the original motivation to look at these currents at all, okay? Then in the solid state physics context, you see that you get these wild fermions in crystals, right? These crystals can have lower symmetry that you would expect in that context, and then you try to see whether there are any manifestations of this type of physics, right? And I mean, this is pretty interesting actually. If it were true, if it existed, it would have been great, right? And then I should mention that at a finite frequency, if you apply this current at a finite frequency, you can actually get a current that is proportional to magnetic field, and that is also related to this magnetic moments that I mentioned, and it was worked out in our paper with my students, and then in Joel Moore's paper on the same subject. Okay, so this is what we call the dynamic chiral magnetic effect. It can definitely exist at finite frequencies. The not fancy way to call it actually is natural optical activity in metals. So dynamic chiral magnetic effect, nature physics, optical activity in metals, PRB. Okay. So this is PRB because, we didn't, hide that it's just natural optical activity, right? So, all right. You're taking revenge, huh? All right. So let me just then show you a few interesting things here. Okay, so let me just make a general remark about, if I want to solve for things in these wireless metals, what do I do? How things are different from what I would do in a normal metal, right? I know how to solve, generalized I. Community knows how to solve diffusion equation. Okay, what's different in here as compared to the conventional diffusion equation? So the difference is really the existence of these chiral currents. So let me just write the equation for the total current flowing in a material. Okay, it has the usual electric current. You see that I put here mu EC, electrochemical potential. So basically, this current involves the usual electric current, sigma times E, right? But it also involves the diffusion current. Okay, and because of Einstein relation, how many of you know what Einstein relation is? All right. Okay. So, okay, no preaching. So basically, you should know what Einstein relation is. These currents basically combine into this gradient of electrochemical potential. Okay, that tells you that the disequilibrium is driven by not electric potential, not gradients of chemical potential, but the gradient of the whole thing, of the gradient of electrochemical potential. That's very important. Okay, and then there is another piece in the current that is described by a chiral magnetic effect. Okay, current that flows along magnetic field proportional to the chemical potential of a valley. Okay, you have it for each valley, and then you see that this involves the chemical potential only, not electric potential. It turns out that even though the the expression for the currents involves only, not the electrochemical potential. The transport equation, the equation for the charge density, involves, of course, the divergence of the current, the continuity equation, but also the anomaly piece, okay? The anomaly piece. And then this divergence of the currents using chiral magnetic effect gets combined with the anomalous divergence. See that there is a appearance or disappearance of charge in the right-hand side of the continuity equation. And actually, they combine to become just the gradient of the electrochemical potential. So you cannot really separate chiral anomaly from chiral magnetic effect. They are kind of, manifestation of the same thing, okay? And they just end up being this divergence of this total chiral currents in the transport equation. So we have the usual diffusion piece. We have this divergence of the chiral current. And then on the right-hand side, I put here what's known as the collision integral, if you will, the collisions between the two valleys, right? So that this equation tells you that the charge can flow around due to diffusion or due to this chiral current, and the charges can go from valley to valley because of scattering, right? Impurities can knock an electron from one valley to the other and back, okay? And if the chemical potentials of these two valleys are the same, you don't have that, right? So the two fluxes cancel each other exactly. If you have different chemical potentials, then there is a collision term like that. So now in the remaining few minutes, let me talk about what I promised you to talk about the observable effects of this chiral anomaly. So maybe let me go briefly around this because it's important for historical reasons, but I think it was very, very hard to observe, and we have a specialist on that in the audience, again, Professor Ong. Okay, so basically, when you think about magnetoresistance, you usually expect the resistivity to go up with magnetic field, which is easy to understand. Magnetic field bends the trajectories, right? It makes it hard to move, okay? Of course, from this naive logic, you expect there will be no magnetoresistance along the magnetic field. There is no Lorentz force that way, except in crystals of low symmetry, there is always longitudinal magnetic resistance too, but it's also typically positive, okay? So you expect resistance to go up with magnetic field, at least in small magnetic fields. Of course, when you're in a quantum Hall regime, resistance can well go down to zero with magnetic field, but this is a regime of a gigantic magnetic field where this simple intuition breaks. So it turns out that in this case of a wireless metal, there is actually a negative longitudinal magnetoresistance, right? You put on magnetic field and it becomes easier to flow along the magnetic field. How does that happen? That happens in the following way. So again, let's substitute this electrochemical potential gradient with just electric field for simplicity. And then basically, I just told you there is chiral anomaly, right? So there is this rate of change of the relative number of particles in the two valleys, okay? So, but that generates the disequilibrium between the two valleys. You see what's going, right? So electrons are coming from this valley to this valley, whoop, okay? So this is a generation process, right? It needs to be stopped by something. If you want to reach a steady state, something needs to stop the generation. So what stops the generation is the intervalley scattering. You go from valley to valley by chiral anomaly, but then impurities become unhappy. They see that there are more electrons here than here. They start scattering you back. Okay, and then there is dynamic equilibrium, dynamic steady state reached, where you have certain chemical potential difference, which is just right to counterbalance chiral anomaly and the intervalley scattering. But once you reached this chemical potential difference, we just discussed that there is a current flowing along the magnetic field, right? Okay, so that means that there is extra conduction along the magnetic field, along the electric field, because it's along magnetic field, okay? So there is extra conduction, the conductivity goes up, so resistance goes down, okay? And this is very, very exciting because you do not see negative magnetoresistance every day, okay? So there are examples in disordered systems, in localization, and this is, the other example, essentially, okay? So everybody got excited, but coming back to this point of this being hard to observe, one thing that is good about this extra conductivity is that it's proportional to the intervalley scattering time. The longer it takes to get from valley to valley, the bigger chemical potential mismatch you build up, the more current you will get. Okay, but there is this, there are these all other Landau levels versus zeroth Landau level. So you essentially get this large three-dimensional density of states in the denominator that tells you that there is only one special Landau level that you use to build up this current, and the rest of them do what you expect them to do. Okay, they are boring, and they kind of fight against you. So it's really like 1 over number of Landau levels under the Fermi surface. So that's what kills you. Okay, and you can think that this is possible to basically get, but then essentially more often than not, the effect is dominated by some completely mundane engineering things known as current jetting, the distortion of current lines in the presence of magnetic field, or in homogeneities. So again, Professor Ong has papers discussing protocols for measurement of this possibly negative magnetic resistance, but it's very, very hard, I take it. Okay, so last 3 minutes. Okay, will you give me that? 2 minutes. All right, but I'll steal that third minute. Huh? Oh no, of course I have, because you took all that time to talk about Wednesday, Friday. All right, that was a very long introduction. All right, so what do you do? If you cannot measure this negative magnetic resistance, what do you do? So one proposal, sort of a rather old proposal from us, with a bunch of other very smart people, was to use non-local transport to detect the anomaly. Basically, in short, you have one pair of leads with current flowing between them. You get chiral imbalance in that region, and then there is chiral imbalance here, and there is no chiral imbalance here, right, in the rest of this film. So this imbalance will kind of diffuse out, right, from under this lead. And if it diffuses away for a substantial distance, if you put on another set of leads here and put on magnetic field, there will be current flowing perpendicular to the film. But if this is an open set of leads, right? So you cannot really have a current. There will be voltage built up to cancel that current with conventional ohmic current, and that's the voltage you measure. So in the presence of this chiral anomaly, chiral magnetic effect, you will have a very, very long-reaching non-local voltages, which will be proportional to magnetic field. And apparently, this was actually measured in a paper some years ago. They saw exactly the same, the predicted sort of decay of the non-local voltage on distances much larger than the widths of the film. But this is in effect. Let me just mention a couple of things. So this is still sort of a quadratic effect in magnetic field issue if you don't have separate magnetic field to operate these leads. So a good manifestation of the anomaly would be something that is odd in magnetic field and linear magnetic field. So the problem with this negative magnetic resistance is it's minus b squared. And everything in the life of metal is b squared, because it's just, it's the first term in the analytic dependence of magnetic field. Everything is b squared. So if you can tune away from that, you can go linearly in B, and not just magnitude of B, which is non-analytic, but still, B to minus B invariance. If you can go linearly in B, that would be great, okay? So there is a couple of proposals by us to measure these effects from this, linear in B plus minus B asymmetric result. One is non-linear transport, which the idea is very simple. So imagine you have two cones. Again, inversion is broken. And these cones have different conductivities, okay? So they're different. Conductivities are different. So if I pass current, the cone with larger conductivity will get hotter, right? Joule heating is larger in that cone. And then when you let them basically talk to each other, the hotter cone will lose electrons faster than the cold one, okay? If you will, there is more phase space for phonon scattering, that type of stuff. Okay, so if the hot cone loses electron faster than the cold cone, there will be actually fewer electrons, and the number of electrons will go down in the hot one to balance that tendency. Boom, you get chiral magnetic effect from that imbalance of chemical potentials, which goes as E squared times B. And the effect is not large, but again, it's much larger than everything else in all possible systems. So this is in principle a test of anomaly. Another proposal, last slide, promise. Okay. Another proposal basically is to use non-reciprocal electromagnetic wave propagation in wireless metals. Basically, the upshot is that in a non-centrosymmetric wireless metal, light propagating that way in magnetic field and light propagating that way will have different refractive indices. Okay, so basically the reflection coefficient from a slab will flip, will change when you flip magnetic field. Okay, this is non-reciprocal dichroism, gyrotropic birefringence. Again, it's all known in the old literature. People knew all that, but it turns out that the effect in a wireless metal is some 100 times larger than the effect in some chiral. I don't know in beets. Okay, beets are chiral. All right. So beets, the vegetable, I mean, that you get sugar from. Right. So just last 30 seconds. It's actually since I wanted to mention on Zaga relations. Basically, the conductivity tensor satisfies this relationship on Zaga relation that essentially comes from macroscopic reversibility of the laws of nature. So if you flip Q and B apart of the conductivity tensor, basically you will get the transposed version of that. Okay, so that means that if you expand in Q and B, there will be a term symmetric in A and B. Okay, which is the usual Drude conductivity. So the linear in Q piece will have eta ABC equal to minus eta BAC. That's the natural optical activity. This is odd in Q, so this has to be odd with respect to A and B. So that's natural optical activity. If you expand to linear order in B, you will get chi ABC equal to minus chi BAC. That's our precious Hall effect. Okay, but then if you expand to linear order in both Q and B, you will get a fourth rank tensor that is symmetric with respect to the first pair of indices. So it's really a correction to the Drude term that is linear both in Q and B. So the Drude term, the reactive part of that omega determines the refractive index, and that tells you basically that if you flip propagation direction, keeping B the same that way or that way, or you keep Q the same, but you flip B that way or that way, the refractive index will change. Okay, and again, this is not a topological effect per se, but in this topological system with chiral anomaly, is just on steroids. Okay, it's just much larger than anywhere else. What does it mean much larger? It's 1%. Okay, it's still 100 times larger than in other systems, and it's very much detectable using present day technology. So let me stop here. I'm done with wireless metals. Thank you for your attention.
Any last burning questions before we move on? Yeah. Just a comment.
Mm-hmm.
When you do see the negative resistance, the effect is huge. When you lower your chemical potential to the last Landau level, which is strictly chiral, the effect is very large. It depresses the magnetoresistance by a factor of 5 or 6.
Okay, so but the semiclassical regime that I actually described, in that regime, it's pretty hard to observe it. I mean, you can still observe huge negative magnetoresistance, except it doesn't come from this wild physics at all.
No, that's not correct. So in this article that you mentioned, we proposed a test for experimentalists, not for theory, that will discriminate between current jetting, which is the trivial non-effect, from the true chiral anomaly. And when you perform those tests, you can filter out the systems that really demonstrate.
Right, that's fine. Right, that's what I mean. That you need to basically work a lot to actually separate it from everything else.
When you do, it's huge. It's not a small effect.
Right. No, I understand that. So basically, the point is that in 2015, basically everybody started getting this negative magnetoresistance. Right. So everybody measured it. So either it was a very, very simple thing to measure, or they were measuring something different, okay? And it turned out to be the latter, okay? Then you have to take special precautions to actually single out that effect that you want.
Okay, thank you again, Dima.